My name is Franco Salviola. I'm the new director of the CRM, and it is my pleasure to welcome you today to the beginning of this fantastic thematic semester in number theory. So this is the CRM. I'm not going to say much about the CRM today, except perhaps that it stands for Mathematical Research Center, but in French, so Centre de Recherches Mathématiques. This was obviously decided before the age of the internet, where you needed a fancy name to distinguish yourself from the other CRMs. You'll learn more about the CRM over the coming weeks, but I just wanted to highlight that there's some fantastic activities coming up. I want to thank the organizers for all the work that they've put in to organizing this event. We have several research chairs coming up, and I'm excited about this activity, and I hope you are too. So I'm going to hand it over now to Carlo Pagano, who's going to take care of the introductions for the rest of the activity. And please welcome Carlo.
All right. And thank you for the introduction and the invitation to be here. I'm really excited at the crowd and the interest, and I think looking for these next couple months, I think are just going to be really fantastic for arithmetic statistics. So I am talking about distribution of unramified extensions of global fields, but I won't quite start there. I'm going to start with the Cohen-Lenstra-Martinet heuristics, which come from papers of Cohen and Lenstra in 1984 and Cohen and Martinet in 1990, and they say let gamma be a finite group and little k be a number field. And they give conjectures about the following situation: as big K varies among gamma extensions of little k. So here we can take that to mean,
special delivery.
Thank you, special delivery of the good stuff. I'm happy to switch. So Galois extensions of, the base number field, whose Galois group is gamma, they make predictions about how the class groups of K vary. I need to add one more kind of piece of data. If you have seen even class groups of real versus imaginary quadratic fields, you know that whether the quadratic field is real or imaginary makes quite a difference in the statistics of its class group. And so for gamma extensions, the same thing is true. So we need to fix the infinite behavior of this extension K that's varying. So I'll say with fixed decomposition groups at the infinite places. So I'll write this here. So these are the places of the base field that are infinite, and let's say for each of those I have some fixed gamma of these. So for each place I have a subgroup of gamma, and I say that is what I want the decomposition group to be an infinity. Of course, we're in the number field situation, so that group should either be a trivial group or a group of order 2 for there to be any such number fields. So now I've stated some family of extensions that I'm thinking about. So they're the Galois gamma extensions, and I say, okay, they have to have certain behavior at the infinite places. And then the heuristics make a prediction about the class group. And so I'm going to leave a little space here because I'm going to add something. But and again, this is heuristic, so this is a conjecture, and it's going to be about the probability that the class group is a particular group, and then give a formula for what that probability should be. Now, there are a few sort of decorations that we need to add to this. So let me just say what A we're considering. So I'll say, since this extension is a gamma extension, the class group has an action of gamma. So the class group isn't just an abelian group, it's a gamma module. So I'll say for a finite gamma module A, and then we're going to predict something about the probability that the class group of K is A. But at some primes, we know something about some part of the class group from something like genus theory or generalizations of genus theory. All of those primes divide the order of gamma. So I'm going to get rid of all of those. So I'll say with A and gamma relatively prime. I'm going to add a prime here to this. So the prime denotes take the prime to order of gamma part. So I'm only going to be asking about this, this part of the class group, the CeLO P subgroups of primes not dividing the order of gamma. And then there's one other thing that could kind of enter the picture pretty obviously at this point and screw things up, which is that the base field itself might have some class group. So obviously if the base field has some class group, that can influence the class group of all of the extensions. So we're going to take here, this is the relative class group, which you can just think of, because we've done this prime kind of naively, as you take the quotient of the class group of the big field by the class group of the small field, but there's other ways to define it. But suffice it to be said, that sort of says, okay, the new part of the class group that didn't come from the base field. All right, and now with all of those caveats, we can give some kind of formula here. So there's a constant that doesn't depend on A in the numerator. Those are explicit in Cohen-Lindstrom-Martinet. And then in the denominator, there's the size of the automorphisms of A, but not just as a group, as a gamma module. And then there is a factor related to just sort of the size of A itself, essentially. So it's actually the product over the infinite places of the size of the part of A fixed, gamma infinity, I should have written gamma V, by each of the decomposition groups that we've fixed. So if you're used to seeing the real and imaginary quadratic case, right, if this gamma V, like in the case of imaginary quadratic fields, was the whole thing, oh, wait, I needed to say one more thing. That's great that I checked the case and then I can make this correction. Then A would have nothing fixed by it, and this would be 1, but if gamma V were trivial, like in the real quadratic case, then this would be the size of A. But this made me realize I need one more thing, which I forgot in my notes. which is that A should have no gamma invariance. And that's related to the fact here that we got rid of the class group of the base field. And so, at least in this prime to gamma part situation, just like you might naively guess from Galois theory, the stuff that is gamma invariant comes from the base field. So, since we got rid of that, we should only be looking for groups that have no gamma invariance. Okay, I think that is a relatively complete statement of that there. You won't find this in Cohen-Lindstrom-Marnay written exactly in this way, but I have a paper with Wei-Tong Wang where we called Moments and Interpretations of the Cohen-Lindstrom-Marnay heuristics, where we explain why they're equivalent to this. All right, now, I need to make some remarks here. One is, I said here, K varies. So there's some question of what that means. What does varies mean? So Cohen, Lindstrom, and Marnay wanted to order the fields by discriminant. Which means that you look at all the class groups where the discriminant is bounded by some x, and you let x go to infinity, and then you look at the limits of those probabilities as x goes to infinity. We now know, for example, by work of Bartel and Lindstrom, that is probably not the right thing. I'll just say perhaps the product of ramified primes is better. But that is exactly how you should order these fields is not going to be the focus of this talk, though there's plenty that you can say about that. Yes?
Don't you have to take some PC notes?
Or like, do you have to restrict the time?
For imaginary quadratic.
Oh, well, okay. For imaginary quadratic, yes, okay. Let's just say you don't take the constant is right. In the imaginary quadratic case, the constant will involve this over all p not dividing gamma. So, all right. Let's just say you're not in the imaginary quadratic case, so you have at least one real place. It's actually right. Unless you were worried about that, like ignore that. But that will technically will technically still be okay in the imaginary quadratic case. But you could also restrict to any finite or infinite low density subset of primes, and then have a corresponding thing here. All right. Oh, so many things to be worried about. Okay. All right. So then the other thing I wanted to say is, I mentioned that something like genus theory can tell us about part of the class group that is not relatively prime to gamma, but it doesn't tell us about all of it. So that there is still, very much interesting going on in the not prime to gamma part of the class group. But that is, not. We'll hear more about that, I think, in other talks this week, and that is not the focus of this talk. So, okay, so Cohen-Lindstrom-Marnay made these conjectures, and there were lots of tables of data that backed them up and made them look like they were very good, very likely to be accurate. But in 2008, started making some more tables and over some different base fields, and he found that in certain situations, these precise predictions that were being made by Cohen and Lindstrom-Martinet did not seem to be so accurate. In particular, they seem to be wrong when the base field had roots of unity of order at primes dividing the size of A. So, for example, yeah, that's always bad when A is even. When you're asking about, the two CLO subgroups, because the base fields always have second roots of unity. Yes?
Another caveat for the bearings that you don't want your K or K bar to intersect with certain cyclotomic extensions.
You're saying that that's a property you want in the bearing. Yeah. All right. I agree. I think I'm not going to go too far down that, but
The order by product of ramified prime should be fine.
that's I guess just to say, so you guys are suggesting that you can think more specifically about what properties you need to make this work more generally, besides a product of ramified primes. But yeah, in any case, even here, if we take quadratic extensions of Q adjoins zeta 3 and look at the three-part Mallet-found issues, and so that means that there's yet another kind of decoration you need to add to this, but it wasn't really clear what it was. So, of course, there are many gammas and there are many primes that don't divide gamma, and so some special cases of Cohen-Lindstrom-Martinet were corrected for roots of unity by Mala himself and work of Adam and Mala and Derek Garten and Lipnowski, Sawin, and Zimmerman. But it was difficult to see what the oh, there's only one board here. Interesting. Okay. Difficult to see what the general case should look like. All right. So I've said all of that, and I'm just talking about class groups. Let me get back to the title of the talk, which was about the distribution of unramified extensions. And I want to say there's a non-abelian generalization of this class group question, where the thing that's abelian here is the class group, which is that this class group, by class field theory, is the Galois group of the maximal unramified abelian extension of K, which of course is the abelianization of the Galois group of the maximal unramified extension of K, which is also a very nice natural group associated to a number field to try to understand. It controls all the unramified extensions, not just the abelian ones. Of course, it is a possibly non-abelian, possibly infinite profinite group, so it's a little bit of a nastier object than the class group, but also important. And so the question here is, how is this distributed? And at least for the work that I'm going to talk about in this talk, it will be a sort of prime to gamma, prime to gamma part. just like we talked about in the class group case. And so we're asking about, okay, how is this abelian group distributed? How are these non-abelian group distributed? And one thing you can ask for, like this, is some kind of formula. Like, what's the probability you get something? But there's another extremely convenient statistic of a random group, and that are certain moments, this is a kind of statistic you can use in all of these contexts, and the moments are indexed by groups themselves, and they're each numbers, they're averages. So the H moment of a random X, where X is maybe a random group, is the expected number of surjective homomorphisms from X to H. So if X is some random group, which you could think of as being a random abelian group, or maybe even a random gamma module, or a random group, or a random group with a gamma action, whatever kind of algebraic object it is, this means surjections in that category of groups, of gamma modules, of whatever structure, whatever, that's why I was a little ambiguous here, whatever kind of thing X is, you mean surjections in that category, and you can ask this for any H, and maybe you hope that it exists and is some finite number, and if it's so, that is it's a convenient statistic of these random groups. I mean, for example, of even the original, when the original Cohen-Lindster heuristics were made, there was kind of one moment that was already known of the distribution for quadratic fields from Davenport-Heilbronn's theorem. They knew the average Z mod 3Z moment for the class group of quadratic fields. Okay, so, all right, so another reason that these moments of these distributions are extremely convenient is because they come up very nicely in understanding the function field analog of these questions. So, I think we're going to hear we'll hear several talks in this direction this week, but there's a program of Ellenberg, Venkatesh, and Westerlin going back to about 2009 to understand these distributions, especially the Cohen-Lindster distributions. In the function field case, even though Cohen-Lindster-Martinet only conjectured about number fields, as was in the title of my talk about global fields, there's no reason to not also think about function fields over finite fields. So in particular in the situation where K is the rational function field over a finite field. And in this program, one wants to understand and then use information about components of Hurwitz spaces, certain moduli spaces in algebraic geometry, and information on the homology or cohomology of Hurwitz spaces. Now, when I first write this, you might think, well, why did you write two separate things? Because components of a space are the H0, that's like the beginning of the cohomology. But in practice, both the input and the output of the work on this is quite orthogonal to the input and the output of the work on this. So mathematically, it really has broken up like this. our understanding here can give Q goes to infinity moments of these distributions, so i.e. those averages, and then conjectures for general ideas about what's going on in the function field or even number field situation. This understanding, this cohomology, as we're going to hear more talks about, allows one to prove these conjectures for, well, depending on what you know, for K equals FQT. If you only know some things about the cohomology, you only can prove some of this, but the more you know, the more you can prove. All right, so that was just to say another reason that these moments were a useful statistic, these averages, because they were directly related to understanding some concrete question of, you could say algebraic geometry or really algebraic topology. Understanding components of certain moduli spaces gave us directly information about moments of these distributions in both the question of the distribution of class groups, like in the original Cohen-Lindstrom-Marnay heuristics, and also in the non-abelian generalization, where you ask about the Galois group of the maximal unramified extension. All right. So, it was in that context that I worked with Yuan Liu, who's here, and David Zurich-Brown, in 2019, and we found, I would say, especially, relative components of Hurwitz spaces. What the relative means is that this whole question of a distribution, there's always a numerator and a denominator. You're sort of averaging class groups over all the extensions. So really, you just need the ratio of the numerator and the denominator to understand things. And so that's why we only needed to understand how many components there were of some Hurwitz space compared to the number of another Hurwitz space. And so we found what, for these groups, Gal K on over K, what these moments should be. And so this gives, for example, gives Q to the infinity. So this is this thing you can do in the function field case that you can't do in the number field case, but you can send this little Q to infinity, gives Q to infinity a confirmation of the Cohen-Lindstrom-Martinez predictions on the class groups. And then for this non-abelian group here, this Galois group of the maximal ramified extension, we had to think, well, what should the conjecture be? There wasn't a general conjecture. Boston, Bush, and Hagier had thought about the cases of quadratic extensions. And so what we did was we thought about, well, what are some things that we know about this group, in particular building on work of Boston, Bush, and Hagier. So we found group theoretic conditions on this Galois group, what it could be, that those conditions led us to propose a random group model that we said is like the non-abelian analog of the Cohen-Lindstrom-Martinet heuristics to predict the distribution of this. And it's we take a free group and we take a quotient by random relations of a certain form. And that form of the random relations is dictated exactly by what we knew, we proved had to be true about this Galois group. And that then proposed sort of random group that we thought should behave like Gal K on over K, given that it matched these group theoretic conditions, then let us make conjectural probability formulas that generalize the formula that I've now erased, but for the probability that the class group is a certain thing. And this model also matched the predicted moments which were the Q goes to infinity proven moments in the function field case that came from our understanding of components of Hurwitz spaces. So this sort of was this nice picture where we understood something group theoretic about Gal K over K. That led us to propose a random group model, which both gave us formulas to generalize the Cohen-Lindstrom-Martinet heuristics to the non-abelian setting, but then also were supported by the by function field evidence, because the components of Hurwitz spaces told us what we wanted those moments to be. And that was all very good story and a nice non-abelian generalization of Cohen-Lindstrom-Martinet. But just like Mala found that there were issues with Cohen-Lindstrom-Martinet when the roots of unity in the base field, our results, in particular, the justification and the matching of the moments with this model, the model requires that you work in groups that are relatively prime in order to the order of your roots of unity in the base field. And so, just to emphasize here, this applies to sort of the second part of the story, not to the components of Hurwitz spaces. We can understand the components of Hurwitz spaces and therefore what the moments of the distribution should be like in all situations, whether or not there were roots of unity in the base field. But we can only understand group theoretic properties of this group that then led us to a random group model where we could get formulas and sort of understand what the distribution was in the case when you were working in groups that were in order relatively prime with the roots of unity in the base field. So sort of really kind of mirroring in the non-abelian situation what one saw already in the class group distribution, that roots of unity in the base field made things much more mysterious. And here, just to emphasize with these moments, in the case when there were roots of unity in the base field, because of our understanding of the components of Hurwitz space, we sort of knew what the moments, what these averages should be for the distribution, but we could not, for the life of us, come up with a distribution that had those moments, and certainly not in generality. like I said here, in some special cases, one can do some things. And so, that leads in to some very natural question about these moments, averages of distributions of a random group. So first of all, do these averages, the expected number of surjections onto various groups, determine the distribution of a random group. And this had, this question has a long history in arithmetic statistics, at least going back to Heath Brown understanding the distribution of two Selmer groups of elliptic curves in a quadratic twist family, and people have used various versions of this. And when I say various versions, remember here, there's some big question like what kind of random object are you talking about? Is it a finite abelian group? Is it a gamma module? Is it a non-abelian group? And what are the moments themselves? Are they large? Are they small? So there are many different aspects here. But in general, there are many specific results that say in certain cases the answer to this was yes. So that's another way in which these moments are really convenient statistics, is often they uniquely determine a distribution. But because of this case where for the Cohen-Lindstrom-Martinet with roots of unity in the base field, or the non-abelian generalization of that, where we have some distribution of groups where we know what the moments should be, but we don't know what the distribution is. A second question is, could we find the distribution from the moments? And I'll say that there's a sort of a couple shades of this question. One is like an existence question. Does there exist a distribution with the moments? But here I'll really more emphasize the, can we find it? Can you actually say what it is? Like give formulas for it. Write it down explicitly from the moments. And so, so now I want to talk about some work with Will Sawin, who is here and will also be talking next on these questions. This sort of general a moment problem. And so the answer to question one, it always depends on the moments not being too big, not growing too quickly in H, but we give criteria for when these moments aren't too big and therefore determine a distribution. And as for question two, when you are in that case, we give explicit formulas for probabilities from the moments. And we do both of these things in a very general category. So, as I've said here, there are many settings in which you might want to apply this. Finite abelian groups or gamma modules or non-abelian groups, so maybe they have a gamma action, and there's going to be more, you know. So we do this in a very abstract setting, so it can apply everywhere. And the idea, I mean, one of the main motivations was to help in this, especially this work in question 2, to help in this setting where one is interested in a random group and has a good guess about what its moments, what these averages should be, but then you want to know, well, what are the probabilities? What are what are those formulas for the actual probabilities? And the basic idea that you might be able to do something like this is not so difficult. So this is the basic idea, sort of for question 2, how you would get the distribution if you knew the moments. So suppose I have some random group, or you can think about whatever random object you want, but X is the random object. I should have wrote it not quite so big. Make it a little smaller over here. And I want to say, well, what's the probability that X is G? But I have only the moments. Okay, well, let's start with, okay, I know the moment, so this is something I know. I know the expected number of surjections onto G, right? So that includes every time X is actually G, it has automorphism of G number of surjections onto it. So divide by the size of the automorphism group of G. Now, I'm not done writing here, but so far what I've written, this is an upper bound, right? Because whatever the probability X is to G, it contributes at least G times that probability to this expectation. So then what is this overcounting by? Well, every time I have some, non-isomorphism surjection from some H onto G, I've overcounted by the probability that X is this bigger group H times the number of surjections from H to G divided by the odd of G, right? Because this expectation, I've divided by odd of G, it included all these other probabilities for all the bigger groups. All right. Now, this might not seem like it helps, because before I was trying to I turned my probability into a P, but it's a good thing because I was running out of space. I was trying to understand the probability that X was one particular group, and I wrote it in terms of a moment, which is a thing that I knew, and then I wrote it in terms of a gazillion probabilities that I don't know. But they were kind of probabilities of slightly bigger groups. They're kind of off a little bit. So what if I repeat? All right, so now I'm going to repeat by plugging into this formula now the same formula for the probability that X is H, where I replace G by H. So I plug in this whole formula again, and now I get a moment for each H. Okay, those are good. Those are the things I know. That's what I want to write my probability in terms of. And then I get a bunch of probabilities of groups that are sort of 2 steps away from G. Okay, so this will look like this term. Minus a term that involves no probabilities, only moments and some other terms, and now a term where I'm 2 steps away from G and I have some probabilities. And I'm not writing all the the terms, just the probabilistic ones. So, and of course, now I can repeat again. And I somehow push the probabilities that I don't know off farther and farther, and writing a formula that is involving just moments at each step. Because whenever I thought it was going to involve probabilities, I pushed them off one step further. All right, so that idea, that's the basic idea. Now, all the work is in making sense of that formally, that this, whatever this was, converges, especially when it's some kind of sum over, things in some quite general category. I mean, with finite abelian groups, you can imagine that you list all the things in a sum like this, but once we're talking about non-abelian groups, there's a lot more work. You can't just sort of explicitly list things in being in a setup where you can make sense of convergence of what this sort of eventually infinite sum would look like if you keep sort of repeating and plugging the formula back into itself. So there are serious analytic concerns. That's what's in the work of our paper. But once you overcome those, what you get is that formally, the probability, or once you overcome those, then it's not just formally, but before you overcome the analytic issues, you can formally sort of write what you would hope, that the probability that x is some particular g is a sum over every, these should all have been surjections. I need 2 arrows on all of these. That should have been. Over all the h that have surjections to g of the h moment with some coefficient, which is not that mysterious. It just involves surjection, numbers of surjections, and automorphisms, and some signs or something. Okay. One extremely convenient thing about these coefficients that comes out of the general theory is that the coefficient is often 0. In fact, it is 0 unless this surjection from h to g is what we call semi-simple extension. And I will just give an example to illustrate what an example semi-simple extension would be, that in the category of groups. If I have an exact sequence like this, or say, okay, so G is a finite group, and V is an irreducible representation of G over Fp, over the finite field Fp for some rational prime P, and then I have an exact sequence of groups like this. So V as a group is isomorphic to an Fp vector space. So it's abelian. So when you have an exact sequence like this, it's a G module. And so when I say V is an irreducible representation of G, I mean in particular with the action of G on this abelian kernel here. And so this is a this is a sort of typical example of a semi-simple extension. You can have actually products of different irreducible representations over different FPs, and you can have a non-abelian generalization of that where FP is replaced by a non-abelian simple group, but more or less this is the thing that you should have in mind. And so that that's a very important feature of our work, because it means that instead of having to think of the whole world of, say, even if you were in the category of groups that might map to your particular group, you now are only thinking of something like all of the irreducible representations of that group over finite fields, or maybe non-abelian simple groups. But those actually turn out to be easier than the abelian ones, so don't be intimidated by those. So it kind of takes the universe of where these sums are happening to a much more manageable place. Basically,
Melanie,
yes.
And I think we're still here in a context where the characteristic of the representation is prime to the order of G. Is that right? Or that's still...
No.
Oh no. Okay.
No.
Oh,
So that would be, if you were in gamma groups, like we were, so this was just in groups, because I'm thinking the general MoMA problem. But if you wanted to be doing Cohen-Lindstrom-Martinet, for example, this would be in the category of gamma groups, and this would be relatively prime to the order of gamma, but not necessarily to G.
Okay. So then I think saying it's just the modular representation is a little bit.
Yeah.
Just.
Yes. Yes.
Sorry, the composite of Q extensions of this form is not allowed. Do you allow like composites of Q extensions like this?
Well, not a composite in that, like, you take an extension like this and another extension like this, in general, no.
But if it's of this form.
But if it were also still of this form, or if it's like a V1 to the E1 plus, V2 to the E2, those are allowed. But not a general do one of these and then do one of those again, no.
It's closed under fiber products over G. So you can take fiber products over G, but not basically that's all you can do.
It just turns out that with these signs coming in, everything else, the coefficients cancel. Using these explicit formulas, and these, we write these coefficients quite explicitly. So Will Sawin and I in 2023, we gave the corrections, gave a corrected version of Cohen-Lindstrom-Martinet from the moments that I had mentioned before in my work with Yuan Liu and David Zurich Brown, and our moment problem work, our work with Will on the moment problem work, which gave explicit formulas to replace the explicit formulas I had on the original board for the probabilities of particular groups. Whenever there were roots of unity in the base field, I'll just mention as I'm erasing here one interesting feature of those probabilities was that sometimes they were zero, which had never been the case. Ignoring the small technical issue that Carla brought up, in the original conjectures, the probabilities always assigned a probability to sort of every, every group, and the corrections just adjusted those numbers. But we saw that the moments predicted some things would happen with probability 0. And we actually proved that all of those things really never occur, even in the number field situation. So that was a big sort of new feature of being able to turn moments, which are positive numbers, into these probabilities, which are sometimes 0. And then you think, oh wait, if we're predicting something occurs with probability 0, maybe we should investigate. Maybe it really never occurs. And so then, in a paper that we have just recently put on the archive, Will and I now think about the situation of the unramified, not necessarily abelian extensions. And so for this Galois group of the maximal unramified extension in the function field case, but allowing sort of relevant roots of unity, we use this work on the moment problem and these kind of explicit formulas that we give to write formulas for a distribution of these Galois groups, and we add an additional piece of data to the group. We add to this distribution of the group that we're interested in also a class in the third homology of this group with coefficients wherever there are roots of unity in the base field. So this q minus 1 is the roots of unity in the base field, and these roots of unity and the existence they allow of this class are sort of what is making roots of unity different. You could say this class comes from Artin-Verdier duality. Artin-Verdier duality says that cohomologically, number fields or function fields over finite fields are like three manifolds. They have a sort of Poincare duality, which is the Artin-Verdier duality, except it has coefficients that are twisted by the roots of unity. But when you have the roots of unity in the base field, it's like the twisted coefficients become trivial coefficients, and that is what is contributing to the existence of this class. So we study the distribution of these groups with this class in their third homology. Will is going to talk more about the kind of topological understanding that needs to go into knowing moments in the category of groups with these third homology classes. I will just end by saying that one uses these formulas. So this is a sort of impressionistic example of what these formulas look like, summed over everything here. I said these are the semi-simple extensions. They're the only ones we need to sum over. We get some kind of sum over all the extensions like this of a fixed group G with some signs and some coefficients. So P here is the P, that V is the irreducible representation of G over FP, with some quantities that came from the moments. So in our case here, these look like the size of H2 and H3 of the extension group here. And so our task is to sort of make sense of this sum. So we'd like to sort of express these in terms just of E, so that we can look at the sum and tell if it does something like absolutely converge. By the Linden-Hochschild-Série spectral sequence and very careful analysis of what happens there for all the different possible extensions of G by v to the E, of which there are many different ones for which these things can differ, we are able to explicitly turn these pieces into group theoretic things that only depend on G and can be pulled out of the sum, and then things that depend only on E formulaically and then can be understood inside the sum. And that is how we sort of get to explicit formulas for probabilities that look in some cases like this, and then we get some explicit formula for a probability, which in this case you can just see, oh, that's positive, and then in other cases you can see, oh wait, that formula is 0. All right, and I will end there.
Thank you very much for the beautiful talk. Are there any questions? Yeah.
Now that you have all the formulas for these probabilities, is there any hope of making a random group model in the rooted unity case?
Well, it depends a little bit by what you mean by a random group model. One could say that, okay, a couple things. One could say that these formulas are a random group model. They give you explicitly a distribution of a random group. Okay, so that's one point of view. Another point of view is that by random group model, you want to process with generators and relations. And there are, for example, in the Pro-L case, Yuan Liu has given a random group model. Now that model, it's maybe from the model a little hard to see what the probabilities are. Before, we used the random group model because they helped us to understand the probabilities. But in Yuan's model, she can, for example, compute the moments. And so now that's an example case where you have a more complicated, but you would call it a random group model with the generators and relations. And it's a more complicated group model, so you wouldn't know its probabilities just from the model, but you know its moments, and you can use this to get the probabilities. So I think that the random group models that are out there, if they are probably sufficiently complicated that even if you did come up with them, I think you would probably use this approach still to understand explicitly their probabilities.
Yeah, but
Yeah.
can it make sense of higher moments in that context?
Well, in this sense, higher moments are just averages with bigger H. Those are the higher moments. And for example, okay, this is only a sort of technical issue if it's only a sort of upper triangular transformation from surjections to homomorphisms. So to answer your question, I'll pretend like I was saying homomorphisms all along. You might think, well, I want to do something like take the square of this, right? That would be the higher moments. But the number of homomorphisms, from x to h squared is simply the number of homomorphisms from x to h cross h. So that's just a bigger group. So all the sort of, the higher moments in the traditional sense are all encapsulated in just taking bigger and bigger groups here. Yes?
That formula for CHG,
Yeah.
and these are positive numbers or not negative?
No, they, yeah, no, they are not. They are, sometimes they're signed. You know, like in this example, you know, there was this sign here. The sign is not so hard to understand.
But the whole sum might be negative. Yeah.
Yes, yes. So for example, if you go back to this question, can you find the distribution, even the existence question, if you are in a situation where the moments are what we call well-behaved, they're not too big, such that it would even make sense to use these formulas. If you compute this formula and you get a negative probability, it means that there does not exist a distribution with that, with those moments.
Yeah, so this is some kind of linear programming constraints, right? Like you have many.
It's kind of not, well, it depends on how you put it. It's kind of not linear programming because it's not, you don't have to find them. If I give you the moments, you just compute one number if it's positive or negative, and you just keep computing numbers if any of them is negative, doesn't exist.
Yeah.
So you're not trying to find a solution, you just have one solution and either works or it doesn't.
Yeah. So
Whereas if you look at classical moments of like probability distributions of the real numbers, there is some more complicated like linear, like quadratic programming condition for the existence of it. You have to it's more complicated to check existence of the classical sense than it is.
yeah, this is just, you have these formulas and, well, okay, you have to be in the context that the moments don't grow too big. But if you're in that context, then you just look at these explicit formulas. If they give you all positive numbers, then that is the distribution and it has those moments. And if any of them are negative, then does not exist a distribution with those moments.
And
yes.
the analytic condition is, you said absolute convergence?
It's a little bit more than absolute convergence of this. In many categories, just a smidge more than absolute convergence of this, yes.
At the end, you mentioned something about textbooks that never happen. Did you show that they actually never happen, or is it just almost never?
Yes. So, in this setting, strictly what we prove is that the things that are predicted with probability 0 never happen unless the extension acquires additional roots of unity over the relevant roots of unity of order prime to the groups that you're asking about, of order not prime to to the groups that you're asking about over the base field. So this kind of a little bit goes back to Julia's point in this question about how are you counting these extensions, presuming that you're counting them in such a way that extensions that acquire additional relevant roots of unity, which only would be at finitely many places, happen 0% of the time, then that wouldn't affect things. But technically, in generality, what we prove is not that it never happens, but it only happens if your extension acquired additional roots of unity.
Okay, it stands for possibility.